I'm delighted to introduce our speaker for this topic, Dr. Sita Sundar Ram. Dr. Sita Sundar Ram has spent the last 3 decades researching, publishing, and then educating audiences of the connections between Sanskrit and ancient mathematics. It all started with her PhD thesis, in which she researched algebra of the 16th century. Since then, Dr. Sita has presented over 30 lectures to universities such as IIT Mumbai, University of Madras, etc., as well as at national and international conferences all over India and South America. In addition, Dr. Sita has presented virtual lectures in 2020 for international audiences. Dr. Sita's focus is on promoting Sanskrit, and to that end, she currently serves as the secretary of the Kuppaswamy Sastry Research Institute in Chennai, the secretary of the Samskrita Academy in Chennai, and as an honorary member of the PS Educational Society in Chennai. Dr. Sita Sundar Ram has a PhD in Sanskrit from the University of Madras. She has an MA in Sanskrit from Karnataka University in Dharwad, and she has a BS in Mathematics from the University of Madras. In today's lecture, Dr. Sita will show 3 things. First will be to show that Sanskrit is not just about shlokas and philosophy, but also about science. Second, she will trace the development of ancient science. And thirdly, she will share with us her knowledge of how technical Sanskrit helped spread ideas. Dr. Sita Sundar Ram.
Thank you so much, Bala, for a lovely introduction. I'm glad to be sharing this with all of you. Yata Shika Mayuranam Naganam Manayo Yata Tata Vedanga Shastranam Ganitam Murdanistitam. Like the crest of the peacocks, the gems and the hoods of the cobras, mathematics is at the top of the Vedanga Shastras. The above statement makes it clear as to how the Hindu society considered mathematics as an integral part of human development. Mathematics, as everyone is aware, has a long tradition in ancient and medieval India. The Rig Veda, the earliest known text, mentions numbers in many places. Ekachame, Tisrachame, Panchachame, says the well-known Chamaka portion of the Rudra. The religious practices in ancient India required a certain amount of knowledge of astronomy and mathematics for astronomical studies and other vocations. For instance, the Vedic man used mathematics to set the auspicious time and to construct the Vedic altars. Next. Thus, we have the Sulba Sutras, which explain the theorem of Pythagoras much earlier to Pythagoras. Ayama Mayama Gunam Vistaram Vistarenatu Samasya Vargamulam Yattat Karnam Tadvido Viduhu. Multiply the length of the right angle triangle by the length and the breadth by breadth. The square root of the sum of these two results gives the hypotenuse. This is already known to scholars. So what is popular today as the Pythagoras theorem was known to the Vedic Indians. Next. Surds Samasya Dvikarani Pramanam Tritiyena Vardayet Tat Taturtena Atmana Taturtit Sa Visheshaha. Root 2 is equal to 1 plus 1 by 3 plus 1 by 3.4 minus 1 by 1 into 3 into 4 into 34. This is given in the Sulba Sutras. Next. How were the numerals represented in ancient India? In ancient mathematics, numerals were represented in 3 ways. As numerals themselves, like Eka, Dvi, Tri, and so on. Next, by alphabets or aksharas. This was called the Katapayadi Sankhya. The third way of representing numerals is called Bhuta Sankhya. Next. The Katapayadi Sankhya is as follows. Kha kha ga ga nga, cha cha ja ja nya represent 1 to 9 and 0. Tata da da na, tata da da na represent 1 to 9 and 0. Papa baba ma represent 1 to 5. Yara lava sasha saha represent 1 to 8. Next. We have the 1,000 names of Vishnu from the Katapayadi Sankhya. Sri Rama Rama Rameti Rame Rame Manorame Sahasra Nama Tattulyam Rama Nama Varanane. Very popular in Vishnu Sahasranama Dhyana Sloka. Here Rama consists of Ra, which is 2, and Ma, which is 5. So 2 into 5, 10. So if you chant Rama 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 3 times, you are chanting the 1,000 names of Vishnu. Next. Melakarta ragas. Many of you may be familiar with Carnatic music, and Melakarta ragas were based on Katapayadi Sankhya. For example, Dhira Shankarabharanam, where D is equal to 9, Ra is equal to 2, and Dhira 92. Using the rule Ankanam Vamatogatihi, so the letters were written on the other way round. So Melakarta is 29. 92 is written as 29, and Melakarta, if you see, for Shankarabharanam is 29. Similarly, Karahara Priya, Ka is equal to 2, Ra is equal to 2, Khara 22, Melakarta number is 22. Next. Bhuta Sankhya. Where were these Bhuta Sankhya used? Most of the ancient Indian mathematical texts were written in Sanskrit and in verse form. The scholar poet has to choose a suitable word to fit in the verse and at the same time represent the numeral. So Netra or eyes would mean 2, Veda means 4, Chandra means 1, and so on. Next. Next we come to the algebraic symbols. So how are these symbols represented in Sanskrit? Yavat tavat kalako nilako anyo varnaihi pito lohitascha etadadyaha avyaktanam kalpita namasanyaha tat sankyanam kartum acharya varyaihi. Now I have given a problem in modern notation. This 6x plus 300 equals to 10x minus 100. 300 equals to 4x minus 100. 400 equals 4x, and so x is equal to 100. But this is represented in the Sanskrit text as Ya 6, Ru 300. Ya is Yavat Tavat. Ru is Rupa, which denotes the constant term. And next line, Ya 10, Ru 200 with a dot on top, which represented the minus symbol. So that's how it is written in our Sanskrit text. Next. Meru Prastara, or the binomial theorem, Pingala, the mathematician of the 2nd century, explains what is called Meru Prastara. So if you write in this form like a pyramid, then each line will represent the binomial coefficients. So first line is A, the second line is A plus B, the third line is A plus B squared, the fourth line gives A plus B cubed, and so on. In modern mathematics, this is called Pascal's pyramid. But Pingala explained it in 2nd century BC. Next. Aryabhatta. The earliest astronomer mathematician whose text is available with us is Aryabhatta. His text is called Aryabhattiyam. Now, Aryabhatta gives the first time the value for pi. Chaturadikam Satam Ashtagunam Dvashashtis Sahasranam Ayutadvaya Vishkambas Nyasanno Vrittaparinahaha. Its circumference is 62,832 and it is divided by the diameter 20,000. It gives approximately the value of pi as 3.1416. What is remarkable is that as early as the 5th century, Aryabhatta said the value of pi is asanna, or only approximate. Till today, It is only called an irrational fraction with circumference divided by the diameter. Next. Aryabhatta is also responsible for the place value system. Ekam cha dasham cha shatam cha sahasram tvayute niyute tata prayutam. Koti arbudam cha vrindam sthanat thanam dashagunam syat. Numerals are as follows: 1, 10, 100, 1000 and so on, as obtained by multiplication by 10 starting from 1. Next. Aryabhatta also gave the area of the triangle. He says, Tribhujasya palashariram samadala koti bhujarda samvargaha. The product of the perpendicular and half the base of the triangle gives its area. The area of the triangle ABC is half into BC into AC. This is what the school children learn these days. Next. Varahamihira, also of the 6th century. As early as at that time, he was not talking about eclipse as the sun or moon being swallowed by Rahu and so on. He gave a very scientific explanation. Uchayam swagrahane bhaskaram arkagrihe pravishiti induhu. At a lunar eclipse, the moon enters the shadow of the earth, and at the solar eclipse, the moon enters the sun's disk. It's a very scientific explanation given by Varahamihira. Next. Brahmagupta should be praised for bringing the zero into the world. He was the first to give a systematic analysis of zero and its operations. In his Brahmasputa Siddhanta, he was the first mathematician who systematically analyzed the concept of zero, negative and positive numbers and their operations. Next. Dhanayor dhanam ranam ranayoho dhanarnayoho antaram samaikyam kam ranamaikyam te dhanam ranam dhana shunyoho shunyoho shunyam. The sum of two positive numbers is positive, of two negative numbers is negative, of a positive and negative number is their difference. Also, 0 added to positive is positive, 0 added to negative is negative, also 0 added to 0 is 0. I have given a small example to prove it also. Now, the discovery of zero by Indians not only helped to establish the place value system, but also to distinguish between negative and positive numbers. George Sifra, in his book, The Universal History of Numbers, says, for thousands of years, people stumbled along with inadequate, useless systems which lacked a symbol for empty or nothing. Similarly, there was no way of conceiving of negative numbers such as -1, -2, -3, etc., such as we nowadays use routinely to express sub-zero temperatures or overdraft in banks. Therefore, a subtraction such as 3 minus 5 was for a long time considered impossible. The discovery of zero swept away this obstacle so that ordinary natural numbers extended to include their mirror images with respect to zero. This breakthrough was realized when Brahmagupta in his Brahmasputa Siddhanta gave rules for zero operation. By opening the way to the generalization of the concept of the number, Ifra says, the Indian scholars enabled the rapid development of algebra. Next. Cyclic quadrilateral. Brahmagupta also gave the area of the cyclic quadrilateral. Bhujayogat tatushtaye bhujona gatat padam sukshmam. Area of the quadrilateral is square root of s minus a, s minus b, s minus c into s minus d, where a, b, c, d are the sides of the quadrilateral and s is the semi-perimeter. Next. Negative numbers have no square root. This was proved by the later mathematicians later to Brahmagupta. Mahavira says, Runam Surupato Avargo Yatas Tasmana Tatpadam. Since a negative number by its own nature is not a square, It has no square root. Bhaskara echoes the same. No moolam kshayasyasti tasya akrititvat. Because, and how was the square got? By multiplying the number by itself. So a by a into a is a squared, or minus a into a is a squared. So the square root cannot be minus at all. It can be only a positive number. That is what it says. Only a positive number can have a square root. Next. Pythagoras theorem. The famous Pythagoras theorem has more than 23 solutions in our Indian mathematics. I have taken one among them. Evam Dipada Triyagmani Shatpada Pashvamani Tasyakshniya Rajjuhu Chatvarimshat Karani. The diagonal of a right angle of which the breadth is 2 padas and the length is 6 padas is root 40 padas. Now you construct the figure like this with a central square and adjoining 4 triangles. So a plus b whole square is equal to c squared plus 4 into half ab. So a squared plus b squared plus 2ab equal to c squared plus 2ab. So cancelling 2ab on both sides, you have a squared plus b squared equals c squared. This is the proof for Pythagoras theorem. Next. Mahavira was a Jain mathematician whose text Ganita Sara Sangraha dealt mainly with arithmetic. This is a very interesting example of Bhuta Sankhya. Analabdi Himagu Muni Shara Durita Akshi Payodi Somam Astapya Shailena tu Gunayitva Katayatvam Raja Kantika Baranam. So multiply 142857143 by 7 and obtain a king's necklace. It's a purely numerical problem. When the multiplication yields 1 followed by 8 zeros and again a 1, it can be represented like a necklace. This is an example using Bhuta Sankhya. The numbers are set down as follows. 3. Anala 3 fires, 4 Abdi sees, 1 Moon Himagu, 7 Sages Muni, 5 Shara, arrows Shara, 8 Sinful Action Durita, 2 Eyes Akshi, 4 Oceans Payodi, Shaila 7. The multiplication yields 1 followed by 8 zeros and followed by 1 like a Raja's necklace. Next. Sridhara is the father of quadratic equation which school children learn even today. Chaturahata samavarka samarupehi pakshadvayam gunayet purvavyaktasya kritehe samarupani kshipyottayoreva. Multiply both sides by 4 times the coefficient of the square root of the unknown and add to both sides the square of the coefficient which belongs to the unknown before the multiplication, then extract the square root. It says, if the solution to the equation ax squared plus bx equals c, this x is equal to square root of 4ac plus b squared minus b divided by 2a. Sridhara's Bija, the text is lost to us, but later authors quote this formula quite frequently. Next. Bhaskaracharya, the golden age of Indian mathematics was reached with the advent of the great Bhaskaracharya of the 12th century. Now the mathematicians are usually divided into pre-Bhaskara and post-Bhaskara. Bhaskara's treatise is Siddhanta Shiromani. He was the first or one of the first to write separate text on arithmetic and algebra. His arithmetic text is called Leelavati. His texts are Leelavati on arithmetic, Bijaganita on algebra, Goladhyaya and Grahaganita on astronomy. Next. There is an interesting story behind the name Leelavati. All conjectures, but it's an interesting story, no doubt. Bhaskara had a daughter called Leelavati. When she was about 8 or 9 years old, he wanted to get her married as was the custom in those days. He was an astrologer himself and found that she could get married only at a particular time, not otherwise. Clocks not being available then, he set the hourglass for the particular lagna. The young Leelavati, playing with her friends, happened to see this and out of curiosity put a pearl inside the hourglass, thereby stopping the flow of sand. The particular time was missed and Leelavati could not get married. Her father, however, trained her in mathematics. In Leelavati, the text, most of the verses are addressed to Bhale Leelavati. Next. So quadratic properties are every quadratic has two roots. Both negative and positives are possible, but sometimes only one root is admissible. In Indian ancient mathematics, all the problems are centered on day-to-day activities. So obviously you could not have a negative of an animal or negative of a flower or a fraction of a man. All these were not possible. That's how the real life problems were used for quadratic equation. Next. So this is an example about swans. Bale Marala Kulamula Dalani Sapta Tire Vilasa Brahmantara Magan Apashyam Kurvancha Keli Kalakam Kalaham Sayugmam Shesham Jalevada Marala Kulapramanam. There was a flock of swans on a lakeside. 7 times half the square of the number of swans were moving about near the lake. One amorous pair of swans was playing in the water. How many swans were there? So it comes to 4. The equation is x squared minus 7 by 2x equals to, it comes to 4 and x squared equals 16. Next. This is a very interesting example about a domesticated peacock and a snake. Asti stambatale bilam tadupri kida shikanti stitaha tambe hasta navoshute trigunas tastamba pramanantare दृष्ट्वाहि बिलम आवृजन तनपतत तिर्यंच तस्योपरि क्षिप्रम ब्रूहि तयोर बिलात कतिमिते साम्येन कृत्योरुतिहि. The peacock is sitting on top of the post and the snake is coming from its hole. You have to assuming that they are both coming at the same speed. At what position does the peacock catch the snake? So the equation that if x is the distance AD, then the sum is worked out, and at 12 units from A, the peacock catches the serpent. Next. The lotus problem, this is a problem on fractions. Amala Kamala Rase Temsa Panchamsa Shashte Trinayana Hari Surya Yena Turyena Charya Kurupadam Ata Shatpir Pujitam Shesha Padmehi Sakala Kamala Sankyam Shikpra Akyahi Tasya. From a bunch of lotuses, 1/3 were offered to Shiva, 1/5 to Vishnu, 1/6 to Sun, and 1/4 to the goddess. The remaining 6 were offered to the Guru. What is the number of flowers offered? So 1/3, x is equal to x by 3 plus x by 5 plus x by 6 plus x by 4 plus 6. So work it out, you get x is equal to. Next. This example has been taken from Mahabharata. Partha Karnavadaya Margaganam Kruddorane Sandade Tasyardena Nivarya Tat Charaganam Nules Chaturbir Shalyam Shatbir Vateshubis Tribirapi Chatram Dodam Karmukam Chichedasya Shirash Sharena Katite Yan Arjunas Sandade. Now he says that x squared by 2 is a group of arrows. 4x were used to kill the horses. 6 were used to down the spear, 3 for the umbrella, flag and bow, and 1 cut off Karna's head. What is the total? So you work out this fraction, x squared by 2 plus 4x plus 6 plus 3 plus 10 equal to x squared. So you get x squared equal to 100. Next. Infinity. Bhaskara was the first one who was able to give a proper explanation for infinity. Till then, any number divided by 0 was called 0. But he said, no, it is not 0, it is infinity by the name Ananta. And he said, the infinity cannot be touched by any other number. You cannot subtract anything from it. You cannot add anything to it. It still remains infinity. And he gives the example of the Lord at the time of destruction and creation of the world. Asmin vikaraha kakarena rashavivi prabhishteshvapi nitsriteshu bahushvapi syal laya srishtikale anante achyute bhuta ganeshu yadvat. Just as the period of destruction or creation of world, though numerous orders of beings are absorbed or put forth, there is no change found in the infinite and inimitable God. So in the quantity which has 0 for its divisor, there is no change, though many may be added or subtracted. So any number divided by 0 is called Ananta or infinity. Next. In modern mathematics, any number, say a by 0, is represented by the symbol like a lying down say 8, digit 8. It's called a lemniscate. It is called Ananta in Indian mathematics. Remarkably, the serpent on which Lord Vishnu is reclining is also called Ananta. Next. This is a problem on combinations. So Bhaskara gives the formula NCR equal to n into n minus 1 and so on into n minus r plus 1 divided by 1 into 2 into up to r equals n factorial divided by r factorial into n minus r factorial. Next. So very interesting example on this about a palace. Ekad vityadi mushavaha Miti manne bruhi bhumi birtuhu harmye ramye ashtamushe chatura virachita slakshna chala vishale. A king had a beautiful palace with 8 doors. In order to get fresh air, 1 door, 2 doors, 3 doors, and so on are opened. How many types of breeze arrangements are possible? The solution is 8C1 plus 8C2 and so on 8C8. That is 8 plus 28 plus 56 plus 70 plus 56 plus 28 plus 8 plus 1 equals 255 ways of getting breeze from the different doors. Next. And permutations also, Bhaskara has given the formula. The number of permutations of n things, taking all at a time, is n factorial. That's the product of n into n minus 1 up to 1. Here's a very interesting example of the weapons of Lord Shiva. Pasankusha ahi damaruka kapala shulehi katvanga shakti sarachapa yuter bhavanti anyonya hasta kalitehi katimuti bedaha shambhoho. Rope, gourd, serpent, drum, skull, spear, club, shakti, weapon, arrow, bow. Next. So, number of different idols of Shiva, holding the different shastras in his different 10 hands is 10 factorial, which is some big number, 36,28,800 ways of you can get idols of Shiva. Next. Prime numbers. Prime numbers do not have a name in Indian mathematics. But an interesting text of the 7th century has been recently edited by a Japanese scholar. The text is called Parikarna Chatushtaya and it has some interesting problems dealing with prime numbers. Ekam trikam panta shatkancha sapta chado pratishtitam trayaschimchat tangunitam kantavarnam adishet. So you have to write 6 threes, 5 sixes and a 7. And when you multiply it by 33, you get a royal necklace. So it is the product of 3 pi 11, 3, 3, 3, 6, 6, 7 and 5, 2, 5, 7, 9. And this big number into 33 is 1, 1 followed by 4 zeros, 1, 1 followed by 4 zeros, 1, 1. So it looks like a Raja's necklace. Next. Krishna's number line. Krishna, the name of the commentator of Bhaskara's work, Bija Ganita, his text on algebra. And for the first time, he got the computation of negative and positive numbers is shown on the number line, which is taught to children in primary class these days. So he calls one side as Paschima or East, the other side as Purva. And he says if you walk 3 yojanas to the to the right and go back 2 yojanas to the left, you have actually covered only 1 yojana. It's actually 3 minus plus 2 equals 1. And similarly, in the third example, you have a person going 3 yojanas to the left and coming back 2 yojanas to the right. How much has he traveled? Only minus 1. This is just to show addition and subtraction of positive and negative numbers. And for the first time in the 16th century in Krishna text, you see the number line. Next. Bakshali manuscript, a very interesting story about the Bakshali manuscript was discovered, or rather the manuscript was found in a mount of excavation of sand in a village called Bakshali in present day Afghanistan. So the British garrison was stationed there, and this village boy who found the manuscript gave it to the garrison. And they could not find any beginning or end of the text. And since it was found in Bakshali village, it is always called the Bakshali manuscript. And again, this Japanese professor has done his thesis on this manuscript, and he has found it has a number of problems on arithmetic. One such problem is 3 persons possess 7 superior horses, 9 ordinary horses, and 10 camels respectively. Each one gives one animal that he possessed to each of the others. They are then equally rich. Find the price of each animal. So you have A has 5 superior horses, 1 horse and 1 camel. B has 1 superior horse, 7 horses and 1 camel. And C has 1 superior horse, 1 horse and 8 camels. Next. So you have to group them 2 by 2 and you get only a proportional answer. So superior horse is to camel is 21 is to 14 is to 12. So since the number of equations are less than the number of variables, you are not getting a particular solution, you get only a proportional solution. Next. Sadratamala is also a text of the 16th century. It is a very small astronomical text, talking about the position of stars and planets and eclipses and so on. But in the beginning chapters, you have a very interesting way of finding the square root of numbers using numbers like 10, 100 and so on to make it easy for children to find the square root of numbers. So let us say you have a square root of 625, which you already know is 25. You just divide it by 10. Then you get a quotient of 62 and then subtract and you just take the quotient, you forget about the remainder. Then divide that by 2. Add it to 10, 62 plus 10, 72. Divide it by 2, you get 36. The second time you do the division by 36 and you get 17. Now add 36 and 17 and you get 53. So 53 you divide by 2, you get 26, forget about the remainder. And the quotient you get is 24. Now add 26 plus 24 is 50 and divide by 2 is 25. So the last time the division is done, there is no remainder. So the square root is 25. Next. Now I have also done research on 2 mathematical texts in Tamil, which is all available nowadays. And I have chosen just 2 problems from them. 10 வயதிலே 8 கூத்தும் 6 திருகும் ஆடுவாளுக்கு சம்பளம் பொன்னென்றால் 5 வயதிலே 4 கூத்தும் 3 திருகும் ஆடுவாளுக்கு சம்பளம் எத்தனை? If a 10-year-old girl will dance 8 கூத்து and 6 திருகு and earn 10 pon, what will a 5-year-old girl dancing 4 கூத்து and 3 திருகு earn? So it is only a matter of direct proportion. 5 by 10 into 4 by 8 into 3 by 6 into 10 is equals to 10 by 8, 1 pen and 2.5 panam. Next. This is also another problem from the same text, Asthana Kolakalam. In a village, there was a Ganapati temple and a garden of flowers. The priest dipped the flowers in the garden and it doubled. So he offered some flowers to the first temple. This he did for 3 temples. How many did he have initially and how many did he offer to Lord each time? I have given the working in the next slide. Next. Let the initial number of flowers offered to God be Y. So in the tank, the flowers became number of flowers is X and flowers offered is Y. So in the tank, the flowers became 2X and he offered to first Ganapati 2X minus Y. And the second time that is become doubled, so 4X minus 2Y. And again he is offering to second Ganapati minus Y, so 4X minus 6Y. In the third time they have become 8X minus 6Y and is offered again Y. So 8X minus 7Y, or rather 8X, he gives everything away, so 8X becomes 7Y. So it is only a proportion. So if the flowers box initially is a 7, then offered to God each time will be 8. If it is 14, then this will be 16. If it is 21, and this will be, and so on. It's only a proportional answer. Next. So this is again only about the denominations, some about the denomination. Ilangail Vedi Suttum Elnutru Kadamundu Vedinil Vidamal Mega Erumbulungai Sellum Valangil Virile Vaitain Vaitili Erimbe Eram Ilangail Vedi Suttum Virangal en Nide. So 12 viral equal to 1 shan, the denominations are given. So the number of fans in so many viral kadai or un kadam will be that big number. Next. Magic square. So this is the magic square. It's very popular in both Sanskrit texts and it is taken from the Tamil text Asthana Kolagalam. The numbers are starting from 1 and go up to 81. So 81 numbers, it's a 9 to 9 magic square. So how do you put the numbers so that vertically or horizontally, they all read the same number? So the method is also given in the text. Next. In the beginning, you take a 1 to 3 into 3 magic square. And how do you put the numbers there? The verse is given. Indiran Vayu Yaman Niridi Pudu Chandirane Shudi Danapatiyam Mundu Kanal Marunan Matridi Karikayar Tangal Inamani N Pattombudurki. So you know the directions: northeast, east, southeast, north, center, south, northwest, west and southwest. And you know the people who are ruling over those directions. Northeast is Ishana, and then you have Indra, and then you have Agni, then Kubera and the center, and then you have the Yama, the Vayu, Varuna and the Nritti. So he says you put the numbers like this. The Indra gets 1, Vayu is 2, Yama is 3, Nritti is 4, center is 5, Ishana is 6, Kubera is 7, Agni is 8 and Varuna is 9. So you follow this and fill the 3 into 3 grid. And then you take it to the big grid. Next. So in the place of Indra, you put the first grid. And then northwest will have the second grid. And then you have the third grid. Where is the third grid? The south is the third grid. And then 27. Then you have the 28. Southwest, you have that. Then you go to the middle, center, and then you go to northeast, and 49. Then you go to north, and then you go to southeast, and the last one will be west. So then you start adding, you get the number 369, I think, will be the number. Each vertical line and each horizontal line will read the same. It is the speciality of the magic square. Next. Now, after the 16th century, maybe due to Islam invasion and British invasion, mathematical texts were few and far between. and even those concentrated in astronomy. But you have one great mathematician, Madhava Sangramagrama, who derived most of the series, infinite series, which became so popular in Europe. So he says tan inverse of theta equals theta minus theta cubed by 3 plus theta to the power of 5 by 5 and so on up to infinity. He's derived many infinite series in his text Venvaroha. Unfortunately, it is not available to us. We have only seen it in being quoted by other authors. Next. Oh, I cannot finish any lecture on mathematics without talking about our own Srinivasa Ramanujam of the 20th century. He was, so to say, discovered by the English mathematician G.H. Hardy, who invited him to England, where Ramanujan did most of his work. Next. So, once Hardy visited Ramanujam in the hospital, and he told him, "Today on my way here, I came across a very dull number, 1729. So Ramanujan replied, "Oh no, it's a very interesting number. It's the only number which can be expressed as the sum of two different pairs of cubes. And can you guess what they are? Now 1729 is equal to 10 cube plus 9 cube. And it's also equal to 1 cube plus 12 cube. And interestingly, 1729 is called the Ramanujan number." Next. We have two other eminent 20th century mathematicians, Sri S.R. Srinivasa Varadan. He was the winner of the Abel Prize, an outstanding mathematician, and Manjul Bhargava, winner of the Fields Medal, who claimed that he was inspired by Brahmagupta's text. Next. Thank you very much, and thank you, Bala, for letting me share my thoughts and some ideas with your dear friends. Thank you very much.
Thank you, Dr. Sita Sundar Ram.